All right, it's been like a year since I worked on this. This is my tiny little operating system. Um, Started as a implementation of this one. It is operating system 1,000 lines. It's like this, tiny implementation of a little toy operating system, and I followed this to learn about how an operating system works, and then I'm doing my own thing. So um, the last thing I did, um, well, so I've just come back to it, over the past couple of days. It's been like a year since I worked on it, but I was working on the file system. So the uh, example operating system in 1,000 lines uses tar as the file system. It's just a single tar file, tape archive. But and that's like really clever, and it's cool, and it's perfect for like what that is trying to do. Like very minimal implementation of an operating system so that you can digest it. That's exactly what I want. But that's not what you want to actually use. It has a lot of limitations. So I switched it over to VSFS, which is very simple file system. That's from the O-Step book. So this book, Operating Systems 3, what is it? 3 Easy Pieces? Yeah. You can find this book online right here. What is WISC? University of Wisconsin-Madison. Okay, so thank you to these guys. Anyway, in there's a description of a file system called VSFS, which stands for Very Simple File System. So the way this works is, it's probably tiny. So your disk image looks like this, right? You have the first of all, it's chunked up into blocks of 4 kilobytes. You have 4 kilobyte blocks. The first one is unused. This is the boot block. So if you're running on real hardware, you have like a boot instructions here how to do that. But since we're running on QEMU, it's just emulated. We don't have a boot block. Then you have an inode bitmap and then a data block bitmap. There's just one bit for each file that says, for each inode, is it in use, and for the data block, is it in use. Then you have the inode table, which is basically all the metadata for inodes. So, I mean, here, I can show you what an inode is. So, what I did first is wrote this little utility that takes a directory and traverses it and just writes out all the directories and files into a disk image of the VSFS file system format. So this is an inode, right? It has its type. It's either a directory or a file. So it has a list of basically pointers to data nodes, data blocks, sorry, and there's direct pointers. So right now it's hard-coded to have only 12. You can have up to 12 data blocks, so each one of those is 4K, so you have 12 times 4K. It's like the max file size right now. And then the size. So yeah, so inode table is just a bunch of these basically in memory. The super block, I think I just skipped when I was describing it. Yeah, actually here it is. Yeah, so there's a super block. There is actually a boot sector before this, but then the super block, which is metadata about the entire file system. So it tells you like where do you find the inode bitmap, the data bitmap. Basically, it gives you all these offsets. What else does it give you? Yeah, it has the magic number of VSFS. How many blocks are like data blocks there are, and the size of the whole file system. Yeah, and then so each of these inodes has like pointers into the data region of like this is where the pages for this file are. So it looks kind of like this. So yeah, that's what I did. So you can write out. So right now, like I have this example file system. This is like the entire disk, right? There's just like a code directory with some code in there. Documents has some stuff in there, and some files. So this utility writes that to a disk image, like this, and then you load that into QEMU. Yeah. So we're kind of halfway between doing that because we wrote out the disk image, and now when the operating system boots up, the kernel like initializes the file system by reading the super block, checking the magic, checking some sizes and stuff, and then that's about it. Like it doesn't actually start loading files until they're demanded, and so that's where I am now with the file system. And I've moved on to working on the shell a little bit because basically what you want to be able to do in the shell is traverse the file system. And so a lot of these things that depend on each other are layered. So I'm trying to take it piece by piece because I'll go to work on one thing and then you need other things in order to do that or to test it easily. So I was going to work on the shell so you can basically just traverse the file system, see what's on there. But one of the main limitations I've run into is I don't have any way to dynamically allocate memory right now. I mean, the kernel has like a page allocator, which just, allocates some pages and maps it, to the virtual addresses for each process. But on the user space side, right, we don't have Malloc yet. So that I started kind of thinking about that, and that's what I'm going to try to implement today. So yeah, that's what we're doing. So I've got some like sketches so far. So this is from the ideas from this is from this book. This is the best fucking book ever. I love this book. Buy this book and consume it. It's amazing. Computer Systems: A Programmer's Perspective. So in here they talk about virtual memory and dynamic memory allocation, and one of the like problems, like assignments in this was to write your own Malloc, and so I did that back when I read this book a couple years ago. So I have a little bit of an idea of how to do that, and you can see my implementation. Isn't it just like CSF? Yeah. So it's section 9. Allocator. So here's like a Malloc. Yeah, so if you care about that, it's right there. Or, get the book and do it yourself. But the idea the important idea there is like how to store like the metadata that Malloc needs, like the state basically, that it needs in order to operate, right? Because like, for example, you want to allocate the interface is just a size. Like you call Malloc with a size and it gives you that many bytes back. But internally, it needs to, store like what's the size of the thing getting allocated. So then when you call free, because when you call free, it doesn't, the interface for free is just like free the pointer. So internally it needs to figure out the size to know how to free and all that. And so all of that data needs to be stored. And so the big idea that this book, teaches you is that you can kind of store this implicit free list within the heap itself. So maybe it's worth briefly discussing like what is all going on when Malloc asks for memory, right? So, I'm implementing an operating system, so you have user space code and kernel space code, and in order for user space to have the kernel do something on its behalf, you have to issue system calls. And so what happens is a process will say, hey, I need some memory. So for example, I'm working on the shell, right? The shell wants to allocate dynamic memory for stuff like arguments that are given to a command line, right? If you wanted to have, say, like a dynamic array of all the arguments, you can store that somewhere. And so one of the ways is to use dynamic memory. You can call some allocator, maybe Malloc, to get a block of memory where you can store these arguments. So, the shell process will call Malloc. Malloc is user space code, right? It's gonna say like, so internally. So this is like the code for Malloc, right? You're gonna have some internal state. This stuff is still a work in process, but when you call Malloc, it's gonna say, hey, do I have enough? Because it's gonna, when you ask, say, for like 16 bytes of memory, it's going to get a whole bunch back and then manage it itself. When I say back, like back from the kernel. So, let's say it's the first time Malloc's being called. You want to get some memory. It's going to call out to the operating system. It's going to, with a syscall. And so, in like Linux, that syscall is sbreak. I'm going to do something similar, but a little bit different. Since all I have right now is like allocating by pages, I'm just going to have a system call called getPages. So Malloc will ask for a certain amount of pages and it'll get that many back from that. Like, yeah, so when it makes this system call, I'll just say, hey, give me like 1 page. Then, in kernel space, it'll handle that system call and say, I'm going to allocate, well, yeah, okay, so this is the interesting thing. It doesn't just allocate those pages and give them back. Right, because we have virtual memory. What it actually does is basically just gives it back an address space that it can use, a virtual address space. So, and it's the same in like Linux with sbreak. It, a process will have like a pointer to the top of the heap, and when you issue a sbreak syscall, all it really does is increment that pointer by however much the caller asked for. I'm going to do the same thing, except for it's in page increments. And so the process is going to have pointers to like the start of the heap and then the end of the heap, like the top of the heap. And when you ask for pages, the kernel will make sure it can do that, and like check that that's allowed, and then increment that pointer, and then give Malloc back the original pointer. So like if this is where the top of the heap is right now, when you ask for more, it'll grow that and give you back the beginning, because that's where you can start allocating to. Okay, I don't know if I explained that well. Hopefully it makes some sense. Yeah, so that's kind of how it works from user space to kernel space. Let's start working on it. So yeah, before I mention that, I was talking about how it like Malloc works. Like, how does it manage the memory actually? And so this implicit free list is how it basically works. So you have like a flat array of memory that you get back from the kernel. And you need to like chunk it up into blocks of like what's free, what's allocated, what's the size of each block. And the way you do that is you have 32-bit header that goes before each block. And what you can also do is have a header and a footer that are the same thing. That helps with coalescing. So like when you free stuff and you want to reclaim that memory so you can use it again, you can coalesce blocks into single blocks, like 2 blocks that are free next to each other. You can combine them into a single large block so that you can put a larger item there. And so having a header and a footer will help facilitate that. I don't know if I'll do that right now. I mean, it's not too hard to change to that in the future. So I think for the start, I'm just going to start putting the header. And so it looks like this, right? You have a 32-bit header. This operating system is for a 32-bit RISC CPU, so it's 32 bits. So everything's going to be aligned to 4-byte boundaries. What that means is for each so what's in the header? There's the size of the block and then 1 bit that says whether it's allocated or not. And so the way you can store all that in 32-bit, because you want to store, like a 32 bits for the size of the block, since it's aligned to 4-byte boundaries, the low 2 bits are always 0. And so you can use those to store anything you want. And one of those bits we're going to use to store whether that block is allocated or not. So you have this 32-bit header, then you have your payload, which is the data, and then possibly some padding if you need to keep it aligned to 4 bytes. And then, this could also in the future, you just copy the header down here, and that's the footer to help with coalescing. And so, when Malloc is called and say, the user says, hey, I want 16 bytes. What you do is you start in the beginning and look at the first header, which is, so there's a special first header that's the prologue, and then a special end of the heap that's the epilogue. So the prologue just gives you a pointer to the first, it has a size and it's never freed, so you always have a pointer to the first block. The epilogue is size 0, but also marked allocated. So if you ever encounter a size 0 block that is allocated, that's, you're at the end of the heap. And so, yeah, when you say like Malloc 16 bytes, what it does is it jumps into that prologue to find the first block. What do you call that? Like, I guess they're just blocks, yeah, the first block. And, checks the size and whether it's allocated or not. And if it finds, maybe there's something that's, 16 bytes or larger, it can use that space. So we'll put it there. But if it can't, then Malloc's going to have to ask for more pages from the operating system. And then it'll have to, make a free block at the end and put the epilogue at the end again. That's kind of what we need to do. So let's start writing some code. So first of all, you need to initialize some data oh shit. Okay, my girlfriend's home, so I need to go talk to her. So I'll be right back. That's kind of a good place to pause. Like I just described what's going on, and then I'll come back and start writing some code. So yeah, I'll be right back. All right, I'm back. All right, so let's start writing some code. Okay, so main things I need to work on is these headers, right? So what I started doing is writing these little macros to access the headers. But what I realized is what you actually want is these would take like a header, which is just 32-bit integer, right? But what you want to actually operate on is pointers to like blocks. So for example, well, I started stubbing them out right here, right? So like you want a macro to put a header, or really put like some data at this pointer, and then a pack macro that's like put a size and an allocated bit into a single 32-bit integer, right? Which is what this is basically. But all right, so let's do. I really don't like these names, but like I can't think of anything better. It takes a size, allocated. And it's gonna give you it's basically this, right? Which says, like, if in this case, if it's a size, you want to clear the low bit, and then set the low bit. So it's going to give you size and not one. The flip, clear the low bit, and set it to allocated. Should be that. Okay. He put takes like a pointer, a block pointer. We'll just call it a pointer because it might be the header of the block. And then what? The data? So I guess you're gonna say like pointer equal data? Why do you need... It's probably because like this can kind of be anything. So do we want to, the question is, do we want to like cast this to U8 pointer? Right? And then dereference it and put the data in there like that? Like, or is this like put a value in there? Like write a 32-bit value. I mean, I guess we're only using this for like writing headers and stuff for now, right? So it's like, so how do we use this, right? So in there we want to put basically 4 bytes and it's allocated. So we're assuming this is like a 32-bit integer. So we cast that to a 32-bit integer type, dereference it, set that to data. We could call that word or like, call it word. Ugh, I hate these names too. It's just bugging me. I'm trying to think of something better. This could be like right word, header right, some shit like that. I don't know. This could be like Header pack. This could be header put. That's assuming we only ever use this for headers, which I think would be true, right? I'm thinking something like that. This should be like a dest. Something like that. Okay, so it's header pack. Put. This is gonna be header right. That's a little better, I guess. So now you need this macro that, like, given like a pointer to a block, find the next block. So the question here is, are we expecting this to be a pointer to the header or the pointer to the data? So we're gonna use this good size thing. Interesting. I'm just thinking, like, is this actually right? Because what we're saying is you have 2 bits down here that you're not interpreting. This one we're assuming 0, but is that always true? Like, what if we want to store somewhere here in the future? So what we should actually do is do, like, 3, right? Because 3 is this value, low 2 bits. So not 3 gives you this. So, like, it's everything but the bottom 2 bits. Wait, is that right? Or... The thing I'm wondering is, like, doesn't this... When you call get size, you need a pointer to a header. Header pointer. So... This is block pointer, this is header pointer. So get the size given a header pointer. So I suppose you want to do interpret this pointer as a 32-bit integer. Dereference it, clear the little bits, that's the size. Get allocated. We do that. So it's just that and one, right? The low bit. So that's if that's, it's either going to be 0 or 1, so that's true or false, yeah. Cool. So let's say we've got this guy, we've got these that all operate on header pointers. And then these operate on block pointers. So hold on. So I do think this is supposed to operate on block pointers, which would mean, right, we need a header pointer from a block pointer. So here you say you just need to step back a 132-bit integer. So that means why am I... Is a header pointer a pointer to a 32-bit integer? Or is it just like a... I think we're dealing with like just byte pointers. Okay. So you have this. You interpret that as a byte pointer. You subtract size, header size. I suppose we should wrap this just in case. That gives us the header pointer, right? So the next block is going to be, you want to get the size of this header from the header. And whatever that size is, add it to BP. But I guess you gotta make sure this is a byte pointer. We have this block P. It could be like header P. Or should we make this block footer? It's just, I want them to be shorter. Whatever. Naming is hard. Alright, so we have that. That's how we get the next block pointer. Does that make sense? So this basically says like, alright, given this block pointer, we're assuming we're pointing at this payload right here. Get the header pointer, so that just back up a 32-bit integer. Then from here we get size, which is gonna just clear out the bottom 2 bits. Right, so that's a 32-bit integer that we're going to add to a byte pointer. So we're going to go that many bytes forward. Okay. So that should work. So yeah, let's walk through what Malloc's going to do, right? So it's lazy initialize, which means the first time Malloc's called, that's when it'll initialize. So the first thing you're doing is you got to make sure you always allocate enough space for a header, right? Because the user of this wants size bytes. They don't know anything about metadata about the block. But Malloc does, so you need to at least that much. Then if you're not initialized, initialize. So the first time it's initialized, what do? You set initialize to true. Figure out how many pages you need, right? So by default, you're going to allocate a page, but if size is like greater than that, you need to ask for more pages. You make a system call to get pages, that many pages, and you get back a pointer to some new memory. So you say some state, how many pages we have, and a pointer to the heap. Now we're using this pointer to step through and set up the prologue and the epilogue. So the prologue is going to be header right into P. It's interesting though, because right now it's pointing to a it's writing into a header, or it's pointing to a header. It's not pointing to the block actually, like the data. That's important because this isn't going to work, this next block pointer. So what do? We write the header there. We step forward by header size. Then we can get the next block. But what we really should do is just make P always point at a block. Because when we go here now, what happens? We need a header right, but now it's pointing at the block, so it needs to be header pointer of P. So that's probably what we should do here, is just we start it off past the header and then write it into, I mean, I just don't like that because it seems a little goofy on the first one. But at least then it's like, I think it's fine. Okay, set up the first regular block. So we get its size. This 2 times header size is to account for the prologue and epilogue blocks. Right, this is now, what do we call it? A header pack? Set up the epilogue block. Well, we went to the next block pointer. In fact, we should call this block pointer so that it's a little more clear. Yeah. Right into header pointer. We're writing size 0. Wait, why don't we just have header right handle, so you give it the pointer and then a size and allocated, and then it packs it for you? That's what we should do. Then we can say that is equal to, you just pack size and allocated. Just be super extra safe here. Shouldn't matter, should it? It's always going to be like just one bit. This might be some stuff. Alright, let's just go with that. Yeah. So you don't need to do the hacking manually now. Honestly. Given a block point, we could just have this all operate on block pointers, right? Where you just say header right, give it a block pointer, it calculates the header pointer. Header right, give it a block pointer. We could do that. Yeah. I don't know why it's taking me so long to get to this. It'd be obvious, I guess. Header right, given a block pointer. So you get the header pointer, interpret it as a 32-bit pointer to reference it, and then there. I think that's better. I like this. Okay. Moving on. So this should set up all of the normal stuff you need. So you have this one giant block that's the first block. Okay, so that should initialize Malloc. So, alright, back in a Malloc call. Now it's definitely initialized. Saying make sure there's space for size, if not ask to allocate pages. So now we need to start traversing this implicit free list. It's really not like well, the reason it's an implicit free list is because it's just a list of all the blocks. Like each of the blocks, given the size, you can get to the next one, which may or may not be allocated. So you just have to walk the whole list to try to find yeah, one of them. So I think what you need is like well, you know what I did in the while reading this book, we did like you try to find a fit and have that block pointer. of size. What I think we really need to do is make a Malloc C file so we can have these internal, so we don't have to like preference them, and we don't have name collisions with shit like some of the. Well, I guess none of those would be. But since it's so simple, I like just having like a single file for it all. We can think about that later. For now, right, find fit, and if you couldn't find a fit, well, now you need to ask kernel to allocate more pages. Assuming it does, now you can you know what I'm thinking now is should we do it the other way? Should we say like if you find it, return it immediately, otherwise, you know, go on and try other stuff? Kind of like having one return location. Well, so if you can't find one, we need to get more pages. So it's basically a copy of what happens here. Kind of, right? Because you're saying... Alright, how many pages do we need given this size? At least one. So you either ask for one page or if size is bigger than page size for that many pages. Okay. The new memory is, well, you can't get pages. Right now we're not handling, like if this doesn't work, the kernel's gonna probably panic, so that's fine. We increment this by the number of pages, and the heap doesn't move because, again, we're dealing with virtual memory, so all the operating system is going to do is just keep getting bigger and bigger numbers, but they're sequential, so you don't have to move the beginning of the heap. You just say we got more pages. Okay. So, and then what we need to do is sort of operate on the epilogue, basically. We need to move the epilogue and then also make a new free block in there. And this would also perhaps be the time that we coalesce. So yeah, maybe we do Malloc coalesce. Right now we're not actually going to do any coalescing, really. By coalesce I just mean like run through the heap and find free blocks, and if there's free blocks next to each other, combine them into single free blocks. I think what I'm going to do to start with is just at the end of the heap, because it just got extended, make a new block that's that size that's free, and move the epilogue to the end. Yeah. Except, what is this now? Like old heap end? What do we do with that information? pass it to Coalesce, because maybe Coalesce needs to know where to start. Probably. Because this is basically going to be where I guess this is an interesting question. It's kind of where the new free block is going to start, except you have the epilogue, the old epilogue's right before that. So you need to like step this new free block back to where the epilogue was. So you're actually going to be like 132-bit 4 bytes back from this old end. But anyway. Alright, we'll coalesce. Did I spell that right? I think so. Coalesce? How do you spell coalesce? Coalesce. Yeah. To come or grow together into a single mass. Yeah. Okay. The thing I'm wondering now is like, should coalesce encapsulate moving the epilogue too? Probably. Here's an interesting thing. So when you find a fit too, because these are kind of connected, what you do after these 2 points, whether you find a fit or you had to coalesce, you'll need to like set some, you will now have a valid block pointer, but now what we need to do is potentially chop that into 2 new blocks, right? Because you could have one large empty block, and let's say you wanted 16 bytes. Well, give them back 16 bytes, but now you need to chop that block into a 16 byte allocated block, and then the remainder is a free block. So, do we have a name for that when we wrote it? We called it place. So like you place. That's a shitty name. We're gonna call it like assign block, or we could say allocate block. I mean, maybe place block. Allocate. See, we don't want to have to like. So allocate a block here, this size. And since we're doing like the same stuff here, well, I guess that's not that much. We could wrap that in a function too. Grow heap. So this is going to be the old heap end minus... Actually, it's not, right? This actually works out really well. This is cool. So the header that was the epilogue, it stays a header. It's just becomes the header for the new block. Right? That's interesting. So Coalesce is going to have to make sure to deal with that, but you don't have to step back because the header for the epilogue becomes the header for the new free block. That's cool. Okay. So let's fill this stuff in. There we go. Something like that. So it's gonna get fucking... Not gonna be able to play any of this music. I'm gonna get copyright striked. Listen to Miss Monique while I eat this Starburst. Okay. Coalesce is really a bad name for this because we're not doing any coalescing, and all it's really doing is moving the epilogue and giving a new free block. And when you actually do coalescing, I don't think you're gonna move the epilogue. So it's really like only ever gonna happen here. So I don't know that we even need to do that. We can do actual coalescing later. But we do need to do these two things in here. I mean, this is the best part of the song, and I just turned it off for you guys. right? So we just subtract header size to make room for the epilogue. Yeah, so yeah, we subtract header size to make room for the epilogue. And then we write new block size and allocated is 0. Which makes me realize up here we fucked up. That's not allocated, that's free. Yeah. Okay, and then, so we've written that. Now we go to the end. Next block pointer from new block, or sorry, old end. So this should send us to the epilogue. Now we just write into BP. Size is 0, allocated is 1. Right. Epilogue. Okay. We should probably just do this. Epilogue is that, and then we write epilogue. Now I don't need comments. That we can still use, I don't know. At least it breaks it up. It makes the scanning easier, right? It's not like you need this comment, but it does make scanning the code very easy. Alright. Then we set that to the old heap end, which is right, and then we allocate a block of that size there. Great. So if we do Malloc, allocate block of size. Basically what you want this to do is write a header for new block of size. Split the block into an allocated block of size and a free block of remainder size. Basically, we want to do that. So, okay. You also need the. We need that. So, yeah, we're gonna right here. Size and allocated. Step forward. No, before we write though, we need to get the old size, so. Old size is header get size. All right. My question now is, should we ever use the header pointer? Or should everything operate on block pointers? Because, you know, what we could do is say like block get size given a block pointer. And then it just calls header pointer. It seems better to just uniformly use block pointers because that's what we're operating with all the time anyway. See, like even in here. I think that's what we want. I guess we can just have both. Although that might be confusing when people are reading through the code, but block get size is just gonna say header get size on header pointer EP. And this is going to be header get allocated on header pointer EP. Right, that was right. It's this. Okay. So the old is now block get size. Yeah, it's a U32. So block get size. That's the old size. We write the new size. We step forward there. What we write here is should this be header right or should this be block right header? Because all of our header prefix things operate on header pointers, right? Probably should be. Probably should, but then it gets longer. Well, we have header pointer too. I don't know, we'll just leave it like this. I don't really like these, but what's the last thing I was doing? This. Okay. So we're writing into here. So this size is going to be I guess old size minus size. And it's free. Right, size is size including the header. So the old size was the full thing. New size, it needs to include, so I think there's a problem here. When we say allocate block of size, oh wait, we do right here align it up to include the header at the beginning, so yeah. I think that's good. So the old size is everything. Yeah, okay. So I think that's right. Basically what that does. Okay, now we need a actually Malloc find fit, which just takes the size, I guess, right? So you can start the prologue and just start looking. So block pointer, if we start at the beginning, that's just malloc state heap. So that is the prologue. So while get allocated, well, that's true. We could just make this a whole for loop too, right? Probably, right? So for that equal that, while this condition is true, next block P, like that. Do we have one too many? Yeah. Go here. We can even do a Muratori style for loop, like so. So you can read that thing. What we want is this though, that. Because I'm using tabs right now, so we want that to actually align. Alright, so you start at the beginning of the prologue. While there's something allocated, hit the next block. And honestly, that does nothing. Or I mean, you don't want to do anything in there. You just keep going until, so actually we need to keep this out, the allocation out. It's like not that wide. But it is more readable like this. Okay. So just keep going until you get one. So if you reach the end, what does that mean? That means if What I'm trying to do now here is check if it's the epilogue. And so you know it's the epilogue if size is 0 and it's allocated. So if get size is equal to 0 and allocated is 1, well, you couldn't find a thing, so we just return null. Otherwise, what I want to do is like assert that this is actually, but I don't really have assert. Right now the assert I implemented is like a kernel assertion that just panics. But in user space code, I guess you should have an assert. Which just what? Like, if it fails, exit the process? We can... Anyway. Now we should have a fit. So just return BP. Oh wait, we actually do need to do something in here. We need to check the size, so... so if get size if it's greater than or equal to size, well, we've found our thing, we just break out. Otherwise, we keep looking. And so just keep on looking until we hit the epilogue. Otherwise, we have one. Okay. Except this is gonna break as soon as there's not an allocated one. So what we actually want to do is just like you actually probably just want a while, and it's like just keep looking until you either get to the end or find one whose size is enough. You shall do this. So yeah, we just want this actually. I mean, we'll just fucking for loop it. Guess you could always step. Yeah, I don't know, we'll do this. Okay. So if it's not allocated and size then we break. Here if size is there and it's allocated, well, we reach the end, we also break there. Honestly, what we could do is return null here, we reach the end. Otherwise, we step forward one. Same thing here. I guess we could return VP. And then this should be unreachable. Once again, I want like an assert unreachable here. But you're going to want to return a route that's going to warn about it. Probably just say that, just in case. Okay. We should probably add like a user space assert. Runtime assertions. Oh fuck, have I been covering up? Hopefully I haven't been operating like where you guys can't see shit over here. My bad. I'm gonna try to use this window now. I'm dumb, I'm sorry. Alright. So we should have found a fit now. Alright, so that's been a lot of fucking code we've added. We need to check if we have... We don't, so we need to expose. These were temporary bullshit wrappers for bullshit syscalls I implemented just to test stuff out. But that was back when we had the tar file system. Yeah, so we just have this. And then we can go ahead and... No, we're not going to put realloc in there yet. Okay, so... Shell's the only program we're compiling right now. It's a fucking mess right now because I'm in the middle of rewriting everything. What we should probably do is take this old hack and just make a new main. Oops, that's just gonna say alright, so just allocate some bytes and show me where we're at. So, oh boy. This is gonna be gross, trying to compile this. I feel like, what's going on in here? A whole bunch of shit. So basically all of this shit. Whoops. What just happened? Just coming out all that bullshit. So we just have that. Does that chill things out at all? So normally I can just F7 in here, but since this is like an operating system, it has like a weird build thing. It has to like build the shell program separately and then load it in as a process. So I can't just like build it. So I can like jump directly to the errors like normal. So I need to do here. Unknown type, so we don't have S32s. Invalid operands to binary expression, U32 and U8 pointer. So next block pointer's not working. This is why macros are gross, because I fucking can't really see. So next block pointer, we're saying header get size. Should I just wrap all this? Plus this thing. Does that work for us? It does work for us. Alright, so Malloc initialized. I mean, let's just do this. Malloc state initialized. Too few arguments to init. We're not doing realloc right now anyway. Alright, looks like we're compiling. Oh my gosh, this is perfect. This is exactly what we want. We want a page fault. That's absolutely perfect. So what should have happened here is we hit called Malloc with a size of 32. We're going to add a header size to that and align it up to 4 bytes, then call init. Init's going to ask for a page of memory from the operating system. It's going to get that back. It's going to set all this stuff up. Wait, what? Yeah, okay. Yep. It's going to set up this list of blocks and all of that and return back a pointer. Well, let's keep running through this, right? So we've set up, we've initialized the state of Malloc. We're going to try to find a fit. Well, the first block is a page, basically, so we're going to find 32 bytes out of that, cut it out, make a new free block, and then return pointer to that block. Then in here, because of this right here, when we try to write the pointer there, actually, I'm a little confused. So what should happen is the second you try to access memory that you just allocated, that's when you hit the page fault. Let me see if this is the issue. Like if we take that out, does it still panic? It does. So this is not quite what we want, I don't think, because it shouldn't page fault until you try to access the memory, and it's page faulting just when it's trying to give them. So probably what's happening is let me go back to the kernel. When we have handle syscall, the syscall for get pages is saying, you know, just make the heap bigger for this. And it definitely is from Malloc, right? Yep. Yep. So something about this, probably because we haven't mapped those pages into the processes space yet, maybe? But this is in the kernel here, so this shouldn't matter. So let's look at this, right? When we do create process, what do we do? Well, you just use the process pool, find an unused one. You put the call these saved registers on the stack because the first time this process is entered context, which happens, popping these registers off the process's stack. Okay, that makes sense. Just setting up so you can do a context switch. You map kernel pages into the first page, and then there's a virtual block device memory mapped IO region, and then you map user pages. Oh, I think I might know what it is. I feel like it's because Malloc is actually touching those pages, right? Because, alright, we said initialize the memory, right? This asks for some pages, great, thanks for the pages, kernel. Then set up a prolog block. We're trying to write values into that memory, so that's where the page fault occurs. That's perfect. And we can verify that maybe by doing this. What if in a init we don't touch that memory at all? So in Malloc, all we do is initialize. And return a null pointer. So all we do in Malloc is initialize, and then in the shell should be a null, but this shouldn't page fault, I don't think, unless there's something else that tries to touch that memory. Yeah, so it still works. We get back in all mine. So what I said, I believe is true. This is actually still working as intended. So as soon as we try to touch that memory, we get a page fault, and the kernel has to handle that. At that point, actually mapping those virtual addresses to physical pages in memory. Yes, 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 yes. It's cool. So this is good. So, in the kernel, what's this page fault called again? Like VMO? scause is store AMO page fault. Don't we have like a scause? Store VMO access fault page fault. This one. scause store AMO page fault. So we have to handle this. Handle trap. So there should probably be a switch case, right? Switch on scause. Alright, so if it's this, and then this becomes default. Break just so it doesn't complain. And now we have a new case. What was it? Store AMO page fault. I really don't like how Vim doesn't like these case statements. We'll just use this so that we can fucking go down. So, if it's a page fault, we need to actually start mapping pages now. The question is, can you get a store AMO page fault when it's not... Like, are there other cases that lead to this, type of situation? Like, you could get a page fault from trying to access a page that you don't have access to, right? That's what like a seg fault is. I think we're gonna have to like look up some spec stuff on this to see like what does this type of mean? Risk 5 supports 16 exceptions. Let me see, store page and risk 5.
If we're only 6 degrees of separation. Traveling to freeze a drop in the ocean.
Okay, so a store instruction or an atomic memory operation has caused a page fault. So I think what we need to do is a few things, right? So yeah. Check if this is valid virtual memory being touched for the first time. I guess we need to check permissions. So, right, there's probably also a read AMO page fault, because if you try to read, is there? Let me see. Load. Load page fault. Yeah, probably that too. Page fault. Instruction page fault, load page fault, store page fault. Yes, so okay. So these are like the same thing. So the permissions you need to check, because you have like, so do we have, if we're in the trap handler, we have access to the current process, right? Okay, let's see. Let's look at map pages because that tells us about like some of the permissions we use. So the page table entry, page number. So who calls this? This is where, okay, so read, write, and execute. Okay. Valid, readable, writable, executable, user, global, accessed, and dirty. So I think we need to use this to um so we need to check. All right, is this memory writable? So scause and stval. What is stval again? Stval. Well, they told us that, right? So I'm assuming that's the pointer. Is that what we tried to write to? That makes sense, right? Because the user user base is that. And that's where the access was. So that's where we tried to write. Okay. So stval is the address. So how do we read these out again? I guess it's basically like that. So stval and page v. So it needs to be valid. Well, in that case, we know you're invalid. Address is invalid. Is it writable? Is this a user? This is the failure condition, or the failure case. So if it's valid and writable, what else could happen? I guess you could check if it's in this process's address space, right? Because trying to think how we would know that. So the stack is just a static. Then you have some virtual memory, which is just right now just used for the code. So you have like BSS, you have code, then the heaps above that. So you know actually the user start, right? User base. And then you know like the heap end. So that is kind of a bounds on your current virtual address space, right? I guess what we want to check here is like, are you trying to write into the heap? I don't think you can check this stuff because these pages haven't been mapped yet, so they're not gonna have. So I guess this is when valid's gonna be 0, right? Because it hasn't been, or the page table entry is invalid. So this is a page table entry, the valid bit. If it's invalid, then you know that it's the first touch. Let's just start with that. This is probably first touch. So we want to do the same thing we do in create process, which is like, allocate pages and map them. So this is the single page fault, right? So you want to allocate the page that this address lies in. So you know you've allocated pages up to heap start, right? So what you could do is you need to find the start of the page that this address lies in. So what I'm thinking is you could align it up to a page size and then minus a page. Basically align down to a page size. Um, so we're going to allocate a page. We're going to mem set page 0 page size. Right, we have that right. And then we're going to map page. We don't have the page table right now, do we? It's the process page table, so current proc, is that what it is? Current proc. Page start. The physical address is page this is you. Readable, writable, executable. So this is a v-adder. stval. Align up to page size. Minus page size. So or we could do a thing where we say like, hey, start at the user base. I guess right now we're making the assumption too that this is like a heap access thing. So we could go ahead and do this. We have a kernel assert that stval is greater than or equal to current proc heap start and less than or equal to, and it's less than current proc heap end. Does my kernel start take messages? No. So right now we're just assuming that it's heap access, right? So align it up to page size and subtract a page. I think that should work. Okay. Allocate a page, clear it, and then map that page into this process's virtual memory. And then what? Well, now you need to like try it again. Well, what happens here? Set program counter to the advance past the equal instruction. So when we switch back to user mode and jump to sub C, we continue after the equal instruction. We want to recall this or retry this instruction. So I don't think we do anything except break. And then I guess we do this. scos strings. So this is going to say it's a story about page fault. Here's this and here's this. Okay. So hopefully this will map the page and then retry the instruction. What the fuck is this? I don't want any of that. So what are we at? What's going on? Oh yeah, this stupid bullshit. In fact, we don't want this yet. We need to end the switch here, yeah. Well, that's a little gross, but that's what you get. I mean, you can do this, but it's still kind of fucked. Which, maybe we should just do that. Alright. What's this warning? Ooh, these stupid fucking, god damn it. Should have known that. Assertion failed. We're not in the heap. Why is that? Wait, handle or yeah, handle syscall. When you call it get pages, you incremented it by that, right? Heap end. Hmm. What's happening? Why is this happening? Heap end is user base plus offset. Yeah. Okay. Handle trap. Heap start. Heap end. Festival. Start. Oh, damn it. And festival. It's the last one. So that makes me think it needs to be equal to. But why are you trying to access? Oh, that's literally the first byte. That's where you would start. That doesn't make any sense. Well, that's one page. What's the first thing we touch in? And like initialize. The first thing we write is a prologue block, which should be ooh, I think I know what's happening. Sorry, handle syscall. I don't think we're... Yeah. We're returning the new end. We want to do the old one. Hold on. For a process, these are V adders. So I guess you can do old heap end is this. Then you say update it and return old heap end. That's the problem. That's the problem. We just continually keep going in there. Okay, well we have changed things. Alright, now I'm getting hungry. Why aren't we writing valid to it? This is weird. How come? Yeah, you're when you map the page, you add a valid thing to it, right? That's really weird. Yeah. Interesting. So we shouldn't have to do this because map page should do that. Page table, V adder, P adder, user read write execute. So yeah, I really don't get this because as soon as you go into map page, we're not panicking, so we get this. The page table should exist already. Page num, and we're explicitly marking it as valid right here. Because that's an address, not a page table entry. Is that why? Yeah, it's this. We need the page table entry for that. I think. Yeah, so this is an address. Yeah. So you're not looking for this. You're looking for um this is so frustrating with this. Okay.
All I want is a piece of your soul
So what do we do? Do we check um
to give me inspiration.
do we check the table 1 entry or do we check both? Cuz right, the page table entry it says this is a page number. Index into level 1, index into level 2, or level 0. Okay. So page table at stval. Sorry. How do we do this? Map page. This. T1 index is stval and v outer page 1 level mass shifted by level 1 shift. So if this and page V so if that's 0, that's what we're looking for. So the only thing I'm worried about now is what if this the address you're trying to access is way outside of the page table. So I need to check if it's even... How do I know? What's the size of the page table? I'm getting a call. Fuck. Alright, I gotta take a call. Hold on. Okay. Yeah, we're back. I was just changing this to actually check the page table entry instead of the raw address because I'm an idiot. So let's see how this works. So we're just hitting this here now. So I don't know if this is happening the first time or if it's mapping it and then the second time it's failing for some reason. It shouldn't get a page fault then though. Yeah, we didn't print this ever. So we do level 1 math, level 1 shift, so this gives us the index. We look at the page table at that index and see if it's valid. So apparently we're getting that this is valid. Okay. I think... Yeah, why are we getting valid here? So idle proc, current proc. So we haven't yielded, so that should be fine. I'm not sure what's going on here. It seems like Does Alec Pages set? It does memset already. So yeah, we don't need to memset twice. Okay, maybe this is why. Ooh. So the user base is here. And way up here, well, it's not that. It's not colliding with that, is it? I was thinking perhaps it's, so there's a memory region for this. There's a page at that address. So one thing we need to make sure we do is is it handle trap? Sorry, I think it's handle syscall. Actually, how do we deal with that? Because the problem is like we have the heap now, which is starting like a little bit after the user base, and then like it's gonna run into this block P address. I guess we can kind of put that wherever we want. Hmm. Page table entry. Alright, what's the fucking entry? So we have this. Alright, so what is this? Well, let's see. Two, 0, 0. D is what? 14? 13. So that's 8, 12, 13, 12, 8, 12, 0, 0, 1. So it's set to valid. It's not readable, writable, or executable. It's not user. It's not global. It's not accessed. Huh. So I need to read up on this virtual memory stuff because it's fuzzy. I don't understand it deeply. But for some reason, this entry in the page table is coming back as valid. Does that mean we look at the one entry? So it's like we've mapped that. Okay, well then we can try. Sorry, map. If we look at map page, this will tell us how to do that. T0 page num. We have this thing. Okay, there's that. Okay, table 0 page num times page size, T0 index, st val. Okay. So table 0 at T0 index. Alright, level 1. Table 1. Table 0 at T0 index. Okay, so just tell me that. Yeah. This one's empty. So what I don't know is table 1 always going to be valid? So the page table, when we create a process, does it always set up table 1? Huh. So if that one is invalid, we do this. Otherwise, I mean, that's why we have the break there, so yeah, whatever. We try this, and we say, basically, if table 0, well, we do the same thing. Back. So proc Malloc physical page. What do you name this? It's like a backup V address with physical address. Like demand paging on demand. Proc vadder. Back with physical page. Oh my god, this is a terrible name. I don't know what to fucking call it. Okay, we do that. In this case, we do the same thing. Okay. So maybe it's that. And once again, we're in a loop of doing it. So why does 0 stay? So it's the first page of the heap. Yeah, what the fuck? Why is this not happening? Map page should literally write an entry into there. Okay. There's something weird is happening. Table 0 is that pointer. T0 index is this. Table 0, T0 index, T0 index. Here. isn't this working? Oh shit. If it's already aligned up, so this doesn't work. So if we align this up to page size, and it's already a page size, when we subtract a page size, we go back. I think we used this trick a few times. No, we don't. Okay. This is our problem. Okay. If it's already page aligned, so page start is just this. Then we have to check. Alright. If that mod page size is equal to 0. So if vadder mod page size is equal to 0, it's just vadder. Otherwise, it's this. I think that's it. That was it. So we allocated memory? Well, I don't know. Looks like we're hung. Maybe we need to write this. What do we do after a trap? Yeah, so, well, we know that it's returning because before. Oh, right. It's just because, well, I don't know. Because you would think we would panic on the. It might be working, but I'm not totally sure. So if we look back here, we could be stuck in this loop. Shit. We are. Yep. We never find. Because for some reason we're not hitting this. Why were we not hitting this? Size 0, allocated 1. Oh boy. Oh boy, oh boy, oh boy. Don't think that's gonna fix it, but just leave this so we know if we're stuck in it still. So, I hate printf debugging. Running epilogue block at here. So writing epilogue block at this, but I think it should be like one before that. So that all seems right. All right. Just, doing some printf debugging, trying to figure out what's going on. Could be my stupid macros. Size 0, allocated 0, so that's the problem. It's not allocated. Header right. Write that one. Why are you not writing that one? Header right. So header pack size allocated. So you take size and not one, and you OR it with allocated. So why doesn't that work? So in this case, the size is what? 0. What? It's all zeros? Wait, why is this hitting it twice? Well, the heap grew. Anyway. The block pointer didn't even move. Is this broken? So header gets size. Hold on. I might need to do this. So it's like, hey, dereference that, and then end it with that. Do we wrap the whole thing then, maybe even? Just more parentheses. This is a Lisp. Header right. So a U32 pointer cast of header pointer BP. Dereference it. Equals that. I don't think that's the problem, but it honestly might be. It's not. So block pointer's not moving at all. Why is that? Why is it initializing twice? It's not. Okay. First block, that makes sense. Okay, so when we write the prologue block, it's here. Its size is 4, it's allocated as 1. That's right. Then we're writing here. Right, block pointer is that, size is that. Yeah, because the page would be 4096, so that's minus 2 headers. Allocated as 0. Epilogue block is here, its size is 0, it's allocated as 1. Then when we get to here, oh man, I think it's because the heap actually needs to point right after the epilogue block. Yeah, god dang it. I think I know the problem. When we start, like, the heap is like this. The prologue is here. The first block's header is here. We're pointing here, and when we try to read, we're backing up out of this. Heap needs to point pointer to right after prologue. Pointer to one header size after prologue block. So init so heap is new memory plus header size. So now we set it to that, right? Yeah. So here, size 0 allocated 1. We get here, size 4 allocated 1, the next block. So we found it. Okay. God, that was kind of dumb, but understandable. So now we can for loop this because we will in fact reach the end, hopefully. Memory. Now we have the memory. We have the memory. So if we write 69 in there, we wrote to memory. We have dynamic memory allocation now. Sick. That's cool. That's really cool. Alright, we can get rid of a bunch of this printing. Alright, we added like a million parentheses that don't matter, but okay. So for this guy, check if HTML entry level 1 page table entry has been created. Check if level 0 page table entry has been created. Basically this. I don't know if we actually have to do those, but that's what we're doing. And then we back it with physical pages by mapping them. Yeah. Sick. That's so sick. Oops. Why are we doing this? Here. Currently assuming this is process trying to accessing memory in its heap. Okay. Okay, that is fucking sick. Okay, we implemented Malloc, basically a poopy version of Malloc. We need to do way more testing, but we have dynamic memory allocation. That's awesome. The next steps are going to be to use that and the shell so we can make a better shell. I mean, we also need to implement like free. What is free turn? Does it give you a pointer back? No. Yeah, so we need to implement free. We need to reallocate, because this is what I actually want for the simple dynamic array, right? If your length outgrows your capacity, you want to reallocate and move members. So what does free look like? I think free is like, well, you go to that pointer, look at its size. In the header, mark it as not allocated anymore, and potentially coalesce it. But for now, we can just mark it as free and not coalesce. And then just say like, you know, there's a block of that size. Take it or leave it. Okay, well, ignore nulls, and then yeah. I guess you do size is block get size p, and then do like header right p size 0. It's now free, and that's about it. Coalesce 3 blocks. Well, now we can kind of free. So let's go to the shell and do this. So we wrote 69 in there. Great. Let's free that memory. Now let's say memory is Malloc size again. This time we set it to 42. Print it again. So it should have the same address, but the value should be different now. That's what should happen. Yeah, we need to put that in the Malloc and free. Boom. We freed it. It has the same address, and it's been reallocated. Alright, we got Malloc and free. We got ourselves a shitty memory allocator. That's so fucking cool. I like that. I like that a lot. Alright, well, we had to, like, get ourselves there kicking and screaming, but we finally figured it out. I'm rusty. I'm rusty. Well, I need to take a break and eat some food, but we implemented Malloc. We got a lot of work to do on it, but it works. Alright, well, that's it for this one. Peace.